Welcome to Mr. Mac's Physics channel. He can explain things really well, and is a lot of fun to watch.
Hi, it's Mr. Mac, and this is the 8th module of physics from the universe to the atom. And we're looking at today inquiry question number 4, which deals with the properties of the nucleus. So here you can see the outcomes from New South Wales Education Standards Authority, and you can see that there are some calculation questions that will come out of this with the new formulae. But you can also see that there's a lot of new work that we'll be able to describe and explain, which is what we're going to look at today. In this unit, the inquiry question is, how can the energy of the atomic nucleus be harnessed? And we're going to learn how to model and explain the process of nuclear reactions. And by the end of this, we will be able to predict quantitatively the energy released in nuclear reactions. So what is radioactive decay? When you have the spontaneous change of an unstable nuclide into another, that is called radioactive decay. The unstable nuclide is called the parent nuclide, and the nuclide that results from the decay is known as the daughter, as you can see from this example, where the parent nucleus is uranium-238. It emits an alpha particle because it's unstable, and then the daughter nucleus is thorium-234. Now, the daughter nucleus may be stable or unstable. Well, how can an atom be radioactive? If the nucleus is more than 83 protons, then it is unstable and radioactive. So if you look at the periodic table of elements and just find all those heavy elements, they are all radioactive. Also, if it has a wrong neutron to proton ratio, it is unstable. An example is if nucleus has 83 protons or less, and there are more protons than neutrons, then it is unstable, as you can see from this graphic. Another example is if a nucleus has 83 protons or less, and there are a lot less protons than neutrons, then it's unstable. Unstable nuclei emit particles, they may be alpha or beta particles, or radiation in the form of gamma rays, until they are transmuted into stable nuclei. If you plot all the stable atoms with the number of neutrons and call it capital N against the number of protons, which is the atomic number, and call that capital Z, then you'll find that it doesn't exactly follow the line N equals Z, as you can see in this graph. A plot of the number of neutrons versus the number of protons for all of the stable naturally occurring isotopes is shown in this graph. And several conclusions can be drawn from this plot. The stable nuclides lie in a very narrow band of neutron to proton ratios. The ratio of neutrons to protons in stable nuclides gradually increases as the number of protons in the nucleus increases. Light nuclides, such as carbon-12, that contain about the same number of neutrons and protons. Heavy nuclides, such as uranium-238, contain up to 1.6 times as many neutrons as protons. There are no stable nuclides with atomic numbers larger than 83. This narrow band of stable nuclei is surrounded by a sea of instability. Nuclei that lie above this line have too many neutrons and are therefore neutron-rich. Nuclei that lie below this line don't have enough neutrons and therefore are neutron-poor. We classify different types of radioactive decay by the radiation produced, as seen in this diagram. Alpha particles are high-energy helium nuclei, and they are positively charged, so when they go through electric field, they are attracted to the negative plate, as you can see, and they're fairly massive. Beta particles, in this case, is a high-energy electron, and you can see it's negatively charged and attracted to the positive plate. But you can have positrons, which are positively charged as well. And gamma radiation is composed of high-energy electromagnetic radiation, which is not deflected at all by electric fields. Here's an example of the decay of cobalt-60. And you can see in the graph how it starts off at 10 grams of radioactive cobalt-60, and the number of half-lives, in this case 5.27 years. After one half-life, half the amount of radioactive cobalt-60 remains on average. Given another 5.27 years, or its second half-life, then 2.5 grams of radioactive cobalt-60 remains. And so we can graph the half-lives, and it looks like an exponential decay curve. Well, binding energies gradually increase with atomic number, although they tend to level off near the end of the periodic table. A more useful quantity is obtained by dividing the binding energy for a nuclide by the total number of protons and neutrons it contains. This quantity is known as the binding energy per nucleon. So the binding energy per nucleon ranges from about 7.5 to 8.8 megaelectron volts for most nuclei, as shown in this graph. It reaches a maximum, however, at an atomic mass of about 60 atomic mass units, or AMU, or simply just U. The largest binding energy per nucleon is observed for iron 56, so Fe56, which is the most stable nuclide in the periodic table. The graph of binding energy per nucleon versus atomic mass explains why energy is released when relatively small nuclei combine to form larger nuclei in fusion reactions. And it also explains why energy is released when large nuclei split or fissure in a fission reaction. So nuclear fusion. What's the difference between fission and fusion? Well, with fission, it's a nuclear reaction where the nucleus splits into two smaller daughter nuclides. With fusion, we have small particles or nuclei that fuse together in a nuclear reaction, and both give out a lot of energy. So with nuclear fission, although fission occurs with unstable nuclei that are large, fusion nuclear reactions occur with smaller nuclei. Here's an example where deuterium, an isotope of hydrogen, with one proton and one neutron, fuses with tritium, another isotope of hydrogen, to form helium plus a neutron. Binding energy is the energy required to break a nucleus into its constituents. The mass defect is binding energy expressed in atomic mass units by using Einstein's equivalence formula between mass and energy. In the fusion process, the combined mass of the nucleus is less than the constituent nuclei which came together to form the nucleus. This mass defect is converted into energy. In general, smaller nuclei have a lower binding energy per nucleon, which suggests that they are easier to break apart compared to big nuclei. Binding energy of small nuclei increases rapidly with size. This is the energy released in the fusion of small nuclei. If a large nucleus splits into two fragments with higher binding energy, then the excess mass is lost and radiated away as energy. In all of these processes, the principle of conservation of mass energy applies. When the atoms lose mass, the lost mass will appear as energy. So here's a worked example to deal with nuclear fusion. And the question is to calculate the energy released in a deuterium-tritium fusion reaction given the mass of a helium nucleus is 4.00153 atomic mass units, or simply U. The mass of deuterium is 2.01410 U. The mass of tritium is 3.01600 U. And the mass of a neutron is 1.00867 U. And the mass of a proton is 1.00728 U. And what's the first step? Well, in any calculation question, the first step is always data. In this case, we're going to write down a nuclear reaction equation where we have 2,1 deuterium plus 3,1 tritium produces in a nuclear reaction 4,2 helium plus 1,0 as a neutron. And we're going to determine the change of mass. Now, this formula is not on your formula sheet, so you need to remember to have the mass of the products minus the mass of the reactants. So delta M equals for helium 4 point whatever plus the neutron 1 point whatever. It's in brackets to show you there the products. And we take away the mass of deuterium and the mass of tritium. Now, if you rounded those to whole numbers, it'll all come out as 0, which is why we use about 5 decimal places. And so the change of mass in this case is negative 0.0199 U. That is, the mass of 0.0199 U is actually all converted into energy. It's a defect. It's a mass defect, which is why it's negative. Now, using Einstein's energy equivalence equation, E equals delta mc squared, we're going to use the delta m. We're going to multiply by a quick conversion factor, and this is on your formula sheet, your data sheet, of 931.5. And so when we substitute in the 0.0199, we can find the answer of energy released in mega electron volts as 18.5369 to 6 significant figures. And now it's over to you. It says worked example. You can find the answer on the other slides that are on the physics website, but this has to do with the sun's energy. This was a question that was in the 2019 HSC examination. And it says use the following information to answer this question. It presents a couple of pieces of data. It gives you the formula for the surface area of a sphere, and it has a radiation curve for the sun that looks very much like a black body radiation curve with intensity versus wavelength in nanometers. And the question is to describe both the production and radiation of energy by the sun. And you've got to include all sorts of wonderful things in your analysis, including calculations, and it's worth a whopping 9 marks. But I'm going to leave that for you to ponder, write down some dot points, see how you go, and then check your answers with the slides. Just to remind you, if you want to find the answers to that, look at the physics website and find the slides, and you can see a solution to that question. Thank you for listening. I'm Mr. Mac.